Hello and welcome back to Calculus 1, section 2.3, Techniques for Computing Limits. So we're going to dig deeper now into how to calculate limits using algebraic techniques, because not all limits will be simply, plug and play or plug and pray, whatever. So techniques are, number one, graph. Number two, chart. And number three, algebra. Now we already covered the graph and the chart. We have to talk about algebra. We will also talk about graph and chart as well, again. Now, why is this important? Sometimes when you try to solve a limit, you will have a 0 in the denominator. And if you just try to plug in the number, as we are used to so far. And at that point, you might say, oh, it does not exist, and then get the problem wrong. So we have to address those situations and take a look at other methods to kind of show that that's valid and right. So the story about approach left and approach right and all of these things with the graphic approach to solving these problems is explained also in 2.3 from scratch, and also the chart method. And they focus on algebra, so that's what we are going to focus on today as well. But before that, we have some properties of limits that we want to write down so that we know how to work with this. So, limit laws. So, number one is the sum. Limit x approaches a of f of x plus g of x is the same as limit of f of x plus limit of g of x. So what this says is that you can separate the limits and compute each one independently. And you have the same thing for difference. Then we have a constant multiple, which is that the limit c times f of x is c times the limit of f of x. So you can kick constants outside in front of the limit. Number four, product. Now, guys, this is a very, very dangerous statement. It works only for limits. It does not work for derivatives or integrals. So you have to be very, very careful in how you use it. Quotient, same deal. power and finally fractional power Ta-da. So those are the limit laws. Do you need to know this? I hope you will know it, because all it says is that you can work on each individual term independently. That's all it is. So no matter how complicated the problem looks like, if you can decompose it and compute, that's great. So let me see if we can find the example. This is a cool example. So let me make up something. Limit x goes to 3 of f of x is, let's say, 10. Limit of g of x as x goes to 3 is, let's say, -2. And let's find one more. Limit x goes to 3 for h of x is equal to, give me a number. 7, thank you. That's good. And if you scream the number when I say that every time, you will not beat the trolls, because the troll's gonna say e to the pi. It's a number. It's like, all right, fine, I'll use it. I don't care. So now what do I want to find? I want to find the limit of 3h minus g over f squared, whatever. All right. So if you look at this, you can break it apart. You first have that the limit x goes to 3 of 3h minus g. Division, limit x goes to 3 of 3h minus g divided by limit x goes to 3 of f squared. So that's further equal to 3 limit x goes to 3 of h minus the limit of g, when we use rule number 2, right, for subtraction. And then I also kick the constant outside. No, that's rule number 3. So I use the rules number, whatever, 2 and 3, yeah. And then on the bottom, I have limit of f, everything squared. So now we know what these values are. Limit of h is 7. So this is 3 times 7 minus -2 divided by 10. That's what? That's what I said. Please pay attention. So I have 21 plus 2 over 100, which is 23 over 100. And that's the limit. We had no clue what the function were, because we were just given that the limit at 3 is 7, that the limit at 3 is -2, and so on. So I use the rules to break it apart, put limit on each one of these as we dig deeper and dig deeper into the problem. So these are all the steps worked out in detail to get 23/100. So those are the techniques when we use the limit laws, if we know, some of the limits for the function. So let's dig into algebra. Limit x goes to 2 of x squared minus 6x plus 8 divided by x squared minus 4. Let me just check the string here. Why is it offline? It's streaming. It gets knocked off. I don't know. All right, so for algebra, we have this situation. Now, immediately what you should do is try to plug in the number. If you get the value, you're good, done. But if you get 0 in denominator or anything weird happening, then you have to do more work. So what happens if I plug in 2? There will be 0 in denominator, right? And that's a problem. So now we have to figure out what to do. And the way to solve it in this problem, in this case, would be to factor everything and see if you can cancel anything. So I'm just going to, here, let me write. We get 0 in the denominator. That means we have to figure out what to do, how to rewrite it. So in this case, we can factor x minus 4, x minus 2, and x plus 2, x minus 2 in denominator, and then you see that these 2 drop. So now what is the answer? Yes? Close? Negative 1/2. So now when we plug in, we'll get negative 2 over 4, which is negative 1/2. That situation when you said 1/2 and he said negative 1/2 reminds me of James Bond. James Bond. Right? It's like half, negative half. Same deal. All right. So this is it. If you know how to factor, you might get lucky and cancel some of these, and that's it. What happens if nothing cancels? We do the chart. Chart is something to fall back on. It's always going to give you an answer, chart. It's just annoying to compute those 6 numbers. It was easy because the previous equation was x squared. Imagine plugging in 2.001, 2.01, right? You're going to type this stuff every time with parentheses and everything else to compute it correctly, right? So you don't want to use the chart unless you must. You try to use the graph if you can, but hopefully canceling and rationalizing and so on will do the trick. Yes?
Wouldn't you have to multiply the denominator of both sides in later problems? Like when we talk about
What do you mean?
Square root.
Yeah, that's going to be rationalizing, sure. Oh, well, speaking of the devil, let's see. Let's make it nicer. Let's use 9 and 3. So limit x goes to 9, square root of x minus 3 over x minus 9. Try. Any ideas? Yes?
I don't know the name of the type of factoring, but I know the formula is a minus b can be written as square root of a plus square root of b times square root of a minus square root of b. It's like the opposite of difference of squares. You know what I mean?
It's exactly the same. It's not opposite. It's
So
exactly
it's
the same.
but instead of using a square, you're just using the 1/2 power, which is the root.
Yes. So this problem can be solved in two different ways. One way would be rationalizing, and the other way would be to use the factoring. Now, I want to use factoring first and explain that, and then rationalizing is somewhat of a kind of standard way if you see square roots floating around. What we know is that a squared minus b squared is a minus b, a plus b. So if I have x squared minus 9, I get to write x minus 3x plus 3. Doesn't matter which order, but the truth is that you can factor anything under the sun. If you have x minus 5, it is going to factor as root x minus root 5, root x plus root 5 because of the formula above. You have to agree that this is a squared and this is a, which is the square root of a squared. So if it's not a perfectly rootable number, you can still leave it as a root. So I can use that here and copy the numerator as is, but the denominator becomes root x minus 3 times root x plus 3. And you see that these guys cancel, leaving you with 1 over root x plus 3, which works out to be 1 over 6. So if you try to plug in a number immediately, you will get 0 divided by 0. Right? And you didn't know that 0 divided by 0 is 1 over 6? Right? Essentially, that's what it is, right? When you divide 0 by 0, you get 1 over 6. So I can make it into any number I want, if I play with functions up there. So technically, knowing this nice factoring that you already know, and by the way, you are the first ever to know that walking into Calc1. So congratulations. Oh, you know? Just be quiet. Oh, I see. Now we have the left side against the right side. It's the left approach and the right approach, right? So it's all right, so what was I talking about? Oh yes, the world. So the way to solve this is to factor it and then do it. But we can also solve the problem if I rationalize. So here's the same problem done differently. I'm going to multiply by root x plus 3, root x plus 3. When you multiply on top, you get x minus 9 when you FOIL, and on the bottom you have x minus 9 over root x plus 3. Those guys cancel, and there's your 1 over 6 again. So what I did is I used conjugate, I rationalized. So this is the one that has a square root. I use the same with the opposite sign. When you FOIL, you will get x minus 9. Root x times root x is x. And then you have plus 3 root x minus 3 root x. They cancel. And then 3 times 3 is negative 9. So now these guys cancel, and you're left with 1 over this. When you plug in 9, 3 plus 3 is 6. So we can solve the problem that way as well. So let's see some of the interesting problems. This is 42 in the textbook. limit t goes to 2, 3t squared minus 7t plus 2 divided by 2 minus t. Yes. How's the factoring? Not a problem? So what are the factors on in the numerator? Right? 3t plus 1 and t minus 2? 3t. Oh yes, you're right. 3t minus 1. Now look what I did on the denominator. I factored out the negative, and then these guys cancel. So now when you plug in 2, you get -5 as the answer. Green? Let's do another textbook exercise. Oh, wow. The example that I used is actually 47, the one with the 9 and the square root of 3. It's actually 47. I don't know what's assigned for homework, so just work around it. Ooh, shiny. Limit age goes to 0. One over 5 plus age minus 1 over 5, everything divided by age.
Find the factors, because that's what I was like confused on. I'm not just you forgetting the factor.
Yeah. That's the, you have to learn the, well.
Because
yeah,
I did the.
where's your pen? Oh, yeah, you can do that.
But then how do you know if it's, plus or the minus?
No,
So I
but
did
you use one number. Because you have two numbers, right? You get two parentheses.
Yeah.
One has 1/3 and the other one has 2.
Okay.
So you will get 1/3 when you use one.
Oh, and that's
sign
how you
and
get
other one. Yeah.
Shit. I was close.
Yeah. We just follow the algebra, right? Do the common denominator for these guys. Keep going. There's the only thing you can do. Find common denominator to subtract these, and then you do the double fraction. There's nothing else you can do. Let's go.
All right, let's take a look. So the common denominator is what? The common denominator is 5 times 5 plus h. So that works out to be, when you cross multiply, 5 times 1 minus 5 plus h divided by h. If it's going to make you better, you can put over 1 to see the double fraction better. So what we achieved here is we added, well, subtracted, right, the fractions, got the common denominator, and now we simplify. This is a very important limit, by the way. We'll do a lot more of this. 5 minus 5 is gone, so I have minus h divided by 5 plus h divided by h over 1. So now to solve the double fraction, we multiply two that are far apart, and then two that are close by. And this is where h drops. And that's what we were after, because we had that 0 in denominator. That was a problem. So now what I have is simple, right? And that is, when you plug in 0, we get negative 1 over 25. Now we have to now wait for the program to restart. That's not a big deal. So there we go. And when we plug in 0 now for h, we get negative 1 over 25. And that's the answer. Good? Problem 34 will take me 3 years to write, so if you want to take like a minute to reflect, you know. So they want us to compute 6 limits for a piecewise function. Function is 0 for x is less or equal than negative 5. Then the function is square root of 25 minus x squared if we have negative 5 less than x less than 5. And then it's 3x for x is larger or equal than 5. They want 6 limits for this one. Okay, let's break it up differently. A, B, C, D, E, F. So we have limit x approaches negative 5 from the left, limit x approaches negative 5 from the right, and limit of f of x for overall -5. Then we have the limit x approaches 5 from the left, limit f of x as x approaches 5 from the right, and overall at 5. So 6 limits for this problem. Okay, so let's talk about this. I will draw this diagram eventually on the tablet, but I can't move it now because the problem is there. So I'll draw on the board and then transfer. So we have -5 and +5 as important values. And if you look, before -5, function is always 0. And then it's the upper half of the circle, going also through 5. And then you have, at 5, you have 3x. So if you plug that there, you get 15. So at this point here, this is open circle. At elevation 15, it's just going to go linear up. So that's how it looks like. And they touch over here. So now if you are looking at this problem, you look at the graph, it's very easy to see the left and the right and all of that if you have the graph. This is why you should know how to graph. Looking at the first 3 problems, say BC, you have -5 from the left. -5 from the left is this, and it's 0. So we have 0. That's the first equation. You can also see that you are using this one over here because that one is to the left of -5. Then you have to the right of -5, which is the approach from the right towards -5, which falls down the half a circle. And you also fall to end at 0. So that's also 0. And by the theorem, if these two are the same, the overall limit is 0. Now on the other side, we are looking at 5. You will go from the left approach down the half a circle, and you will end at 0 for the first. But for the right approach, you are traveling down the linear piece all the way up on top, and that one ends at 15. So now you have the left and right to be different numbers, which by the theorem that we had last class does not exist because the left approach and the right approach do not match at the same point. Fair? All right. So now I'm going to draw this diagram and then we'll take a look at something else. Yes. Well, that's true, but I also have -5 closed circle here, which plugs in. So if I draw the half a circle first, let me now graph the function, and I will address your question actually while doing so. So if I put the open circle and connect with half circle, you would agree on this, right? And now I add the 0 part. That's what fills the circle. When I add the 0 at -5, had the closed circle, so it plugs in. And that means that they are perfectly connected. We call that continuous. That's going to be our 2.6. So because it plugged in. Now, this is elevation 5. This is 5. And then here, let's say right there is the closed circle linear piece at elevation 15 on the y-axis. So I said we have the red approach, blue approach, and blue approach to see all the zeros and values. Cool. With a smile. It's calculus. You should be happy, you know.
So if we look at this, for A we just looked at 0. For B we looked at the square root of 25 minus x squared. And then for b, we look at again, the 25 square root of 25.
Yeah, but why?
I just want to know.
Yeah, but why? Why did we look at that?
Because it falls in between.
Yes. So,
Visually, for 5, half a circle is left. And for negative 5, it's right. That's the part.
so once we draw the graph, now how did I know it was a half a circle? This 25 minus x squared. I know, but if I get negative 5 and positive 5 and this one, can I just make a triangle? Because it's under square root that smooths it out. Okay. The answer we just know. Nice. Okay. One more concept. It's called the squeeze theorem, and 2.3 is over. You already know squeeze theorem? You like it? No? You really like it? Why are you bothering? Oh, we can't do anything without this. How are you going to do Calc 2? All right, how many of you have to take Calc 2? Oh, look at that. Okay. You know what? We're gonna take a second break to jump into Calc 2. 8.1. Look at this. Hold, wait for it. And now look, every single problem. Limit, 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 limit. And then as you jump into every single section, it's gonna be limits everywhere. Every single section will have limits. It's hard to spot them because I'm going a little bit fast, but half of Calc 2 is taking limits all the time. There is no, I don't like this. You gotta love it. Okay, here's what you're going to do. You wake up every morning and you say, I love limits. You know it's a lie, but that's okay. Eventually, you start believing the lie. If you say it enough times. And then maybe you might start living the lie. That's awesome, right? So you wake up, I love limits, right? Love limits. And then we go on. You gotta do it, man. It's just, such is life. All right, so we have the squeeze theorem. Also known as the sandwich theorem in some textbooks, depending on which textbook you read. That's another name. And you're literally sandwiching a function in between easy functions to figure out what the limit is. So first I'm going to write the theorem for the squeeze theorem, and then we are going to take a look at, let's say, 2 examples, and 2.3 is done at that point. So the squeeze theorem. Theorem goes like this. Assume that function f of x is smaller than g of x and smaller than h of x. For all values of x. Near a except possibly at a. And here's the theorem computation part. If the limit on f going to a of f of x has the same value as the limit x goes to a for age of x, then the limit, oh, all of that, oh, I don't have the room there. All right, switching it down. I'm going to write the same thing. You don't have to kill anything. So if limit x goes to a of f of x is the same as the limit x goes to a, the age of x is some value L, then limit x goes to a for g of x, which was the evil function, is also L because it's sandwiched in between. You can see it's over here. It's sandwiched in between f and h. So if you are able to sandwich this bad g of x in between f and h, and you can show that f and h have the same limit, then the one that it's squeezed in between has to have that limit as well. I don't know if it sounds like common sense or not, but if I have two pieces of bread and I place a slice of cheese in between, if you are lactose intolerant and put two slices, wherever I move those two pieces of bread, the cheese will go with it. So one piece of bread is f, and then you have the g, which is cheese, and then you have another piece on top, which is the h. You grab for f and h, g is squeezed in between. Wherever you bring the bread, the cheese goes with it. It's sandwiched, it's squeezed in between. So what do I mean move it? This L is like a location, the answer. So if I move the sandwich here, that's where the L is, and the cheese is there as well. So it's on the same location. Now, if I have a piece of bread and I put cheese on that thing and another piece of bread is here, so you have different limits, then clearly it doesn't work. Which, when I separate the pieces of bread, then this equal is ruined here. They don't have a common L, so this one will not have the common L, because there's no common L. But only if I sandwich it like this, and I take it places, no matter where I put, it's always going to be the same value. So now, this is used for, certain difficult problems. Like here's the beautiful limit. They give us very few of these exercises. Look how beautiful that is. It's amazing. You have 1 divided by 0. How much is that? Right? 1 divided by 0. And then you take sine of that, and you multiply it by 0. Wow, amazing, right? How do we solve these problems? Well, I have to engineer two functions that are going to squeeze this in between. I start from a notion that sine function is bounded. Sine function is bounded. We write that as absolute sine x is less or equal than 1. Meaning that sine 1 over x is sandwiched between -1 and 1. No matter what kind of function you have, the sine can only spit out values between -1 and 1. You know how the graph looks like for sine. It's a wave. The most it can give you as the answer is 1, and the least it can give you as the answer is -1. So sine is bounded, it's sandwiched in between -1 and 1. That's what the bound means. And you put that in these absolute values because that's a compact way. Now I have sine of x over here, I have sine over 1 over x. You can have whatever the hell you want here, it doesn't matter. Once you compute the function, when you take sine of that value, you will get a value between -1 and 1. So we don't concern ourselves with what's here. It's completely unimportant, right? You just copy whatever you have. So now you are comparing these two, and you realize that you are missing the x squared, right? So the next logical step would be to multiply all three sides of this inequality by x squared. Oh, come on. Once I multiply all three sides by x squared, I just compute it, simplify it. And look what I found. I found two functions that I didn't know before. That's your f of x, that's your g of x, original problem, and this is your h of x. So now, using the squeeze theorem, I will find the limit x goes to 0 for -x squared, and that's what? Very good. On the other side, limit x goes to 0 of x squared is what? 0, and now by squeeze theorem, must be 0 because it inherits the same value. If I had the ta-da button, I would just push it now. So we engineered these functions. And you engineer them by starting from the, you're going to have issue with me walking over here, I see. So you start by some bound, and then you keep multiplying to match the functions to look the same. The graph for this is awesome. Here's the graph. And this problem is done. I do very few problems that are solved in a book. I like to do problems from homework because the ones that are solved in the book, you can read, right? You know all the letters. You just read them. The black function there is the g, is the bad one, the sine of 1 over x. And look what it does. See how busy it gets around 0 over here? It oscillates infinitely fast. So good luck figuring it out. The red and the blue are your f and g, positive x squared and negative x squared. So you see how those, they act as bread, right? And the sine function, the wave in between is the cheese. So you see how they all fall to be 0 at 0, right? And that's why I live in. Had enough? All right. All right, so that's 2.3. We are done with 2.3. And there any questions, concerns? Should we do another one, squeeze theorem? Do I have anything on the squeeze theorem? Maybe we do another one, huh? You're gonna love this one. Use negative absolute x less equal than x squared ln x squared less than equal than positive absolute x to solve. I paraphrase the problem. Doesn't matter. Oh, you can't see what I'm writing. That's why. That's why you're complaining. There we go. Much better. Just go spray Alex. I'll be right back. I can hear him on the hallway.
He literally does the hardest problem, but the homework stuff is bad.
So the answer is 0? For every answer is 0, right? Easy. Unless I make it to be like 3. It's a problem. But yeah, limit x goes to 0 for negative x squared is 0, which is the left bound. This one is also 0. And then what's squeezed in between must inherit the same limit. So that's the point of squeeze theorem.
That's all we would have to do for that problem. Like, that's what we have to show. Just prove it.
Yeah. Are you disappointed?
No.
Sorry. Such is life.
I wasn't disappointed.
All right, so that concludes 2.3. I'm going to stop the stream. Bye, stream.